In our last video, we talked about odd electron molecules, and we said that so you can put the odd electron, like I think we talked about NO, and we said you can put the odd electron on the nitrogen or you can put it on the oxygen. It doesn't really matter. Okay, today we're going to talk about how we know which is the better way to represent that molecule. So I'm going to write NO over here on the side just to kind of help me remember not to forget about it. So when you draw a Lewis electron dot diagram, one of the things that you can do is you can calculate what's called the formal charge on each of the atoms, okay? And the formal charge is basically what charge would each of those atoms have if each of the valence electrons and the number of electrons surrounding it were combined together. And by that I mean basically to calculate the formal charge is you look at the atom and then you count the number of valence electrons that atom has. So just like when we did Lewis electron dot diagrams, you look at the periodic table and you go, for example, oh, carbon. Okay, carbon has 4 valence electrons because I look at the periodic table and it's in the column that has a 4 above it. So for carbon, carbon has 4 valence electrons, and then you subtract the number of surrounding electrons. Now this is the part that you got to think a little bit about. If there's dots, you count each dot. Okay? If it's a bond, though, you only count 1 electron from each bond. Basically, it's like you cut the bond in half, and there's an electron here, and there's an electron here. You only count 1 of those. So let me show you what I mean by this. So carbon has 4 valence electrons, and we're going to subtract, again, the number of surrounding electrons. Carbon doesn't have any dots on it, but it does have 1, 2, 3, 4 bonds. So we're going to subtract 4. That means that carbon atom has a formal charge of 0. And all of this that I'm explaining is down here below as well, by the way. Okay, in terms of oxygen. Oxygen, the first thing I do is I go to the periodic table. And I go, oxygen has 6 valence electrons. And then I'm going to subtract, again, count here with me, 1, 2, 3, 4. And again, I cut that in half, 5, 6. Okay, I don't count the ones over here. I just count the bonds. Oh, so basically you count the dots and you count each bond as 1. Each single bond is 1. A double bond counts as 2. A triple bond counts as 3. Yes. 6 minus 6, 0. Okay, what that means is that none of the atoms here have any formal charges. Well, why does that matter? Because that is the best representation of the molecule. If I give you 2 different molecules and I say which one is the better representation of the molecule, the one that has no formal charges or the least formal charges, this is what I'm talking about right here, is the better way to represent that molecule. Okay, so yesterday when we talked about NO, let's look at 2 different ways we can draw that. NO has 6 electrons all total. So I'll make nitrogen the central atom this time. There's 8, 9, 10, 11. Okay, and now I need to bring, because that nitrogen only has 5, I'm going to take 2 electrons off the oxygen, and I'm going to make a double bond. Okay, that's one way to draw NO. Okay, another way to draw NO is making oxygen the central atom. So nitrogen has 8, 10, 11. Okay, and then again, same thing. I'm going to take 2 off the nitrogen and make the double bond there. Okay, now if I ask you on a test, which is the best representation of the model, and I say justify your answer in terms of formal charge, it means that you have to calculate the formal charge of the atoms in both molecules, and then again, whichever one has the lowest formal charges, that is correct. Okay, so let's start with this one over here. Let's start with oxygen. Okay, so oxygen again has 6 valence electrons from the periodic table, and then I count 1, 2, 3, 4, 5. Okay, 6 minus 5 is positive 1. And what does that mean? It means that the oxygen atom has a formal charge of positive 1. So up in the corner, I'm just going to put a little plus with a circle around it. Okay, and that's showing that oxygen does have a formal charge of negative 1. Okay, nitrogen, on the other hand, again, the first thing I do is I look at the periodic table. I see that nitrogen is in the 5th column, so it has 5 valence electrons, minus 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. Okay, so that means that the nitrogen has a formal charge of negative 1. Okay, our nitrogen, our NO on the other side, though, again, oxygen has 6 valence electrons minus, count them up, how many dots does oxygen have and how many bonds? Again, all total, 6. 4 lone pairs, or 4 electrons, and then 2 in the bond, so that's 6. So this one has no formal charge on the oxygen. Nitrogen, again, 5 valence electrons minus the 3 electrons plus the 2 bonds makes 5, so 5 minus 5 is 0. Okay, so the molecule on the right has a formal charge on the oxygen and on the nitrogen. The molecule on the left with the odd electron on the nitrogen has no formal charges. So what is the best representation of the molecule? This one. Okay, and how would you justify that? How would you explain that? You would explain that by saying that the NO with the odd electron on the nitrogen is the best representation of the molecule because there are no formal charges on any of the atoms. Okay, and that's all you'd have to say. Okay, let me show you another example. Okay, SO42 minus. Okay, SO42 minus can be drawn with 4 single bonds or 2 single bonds and 2 double bonds. So I'm going to draw them both. So one way to draw SO42 minus looks like this. And then the other way to draw SO42 minus says that you can have double bonds. Okay, on 2 of them. Okay, now the problem here is, wait a minute, Mr. Johnson, the one on the right doesn't obey the octet rule, the one on the left does. Anytime you're talking about formal charge, forget about the octet rule. Okay, if I ask you to draw a molecule and I don't say anything about formal charge, you don't ever even think about formal charge. The only time you think about formal charge is when I use those words exactly, formal charge. That means when I say formal charge, I mean forget about the octet rule, only think about formal charge. Because you're exactly right. The one on the left does obey the octet rule, the one on the right doesn't. Sulfur many times does have an expanded octet though. So again, in this case, we don't even care. Okay, those are 2 different ways to draw SO42 minus. And so in this case, forget about the octet rule. We're only going to focus on formal charge. Okay, so at this point, pause the video, see if you can come up with the formal charges for all of the, let's start with the left-hand side here. Okay, so start with the all single bonds, do the formal charges for all of those atoms, okay, and then come back and then watch me do them and see if we have the same answers. Okay, so for the oxygens, now all the oxygens are the same because they all have 1 single bond and have 6 dots on them. So oxygen again has 6 valence electrons, and then we're going to subtract the 6 dots plus the 1 bond. So that's 6 minus 7 is negative 1. So every single oxygen has a negative 1 formal charge. Okay, and then the sulfur in the middle has also 6 valence electrons based on its position on the periodic table, and it has no dots on it, but it does have 4 bonds, so then we're going to go minus 4. Okay, so that means the sulfur has a charge of positive 2. Okay, and hey, all right, I'm just doing what I'm told. The one on the right, though, this oxygen here and this oxygen here both have just the single bond, and it's actually the same as all the oxygens over on this side. So that's a minus 1, and that one's a minus 1, because again, 6 minus 7 equals negative 1. Okay, but this oxygen here and this oxygen here, again, 6 valence electrons minus the 4 dots plus the 2 bonds makes 6. So that's a 0, and this one's also a 0. And then the sulfur in the middle, again, 6 valence electrons minus 1, 2, 3, 4, 5, 6. Minus 6 bonds is also 0. Okay? So, which one is the better representation of SO42- based on formal charge? Absolutely, it's this one on the right. Okay, and again, all you would have to say is it's the one on the right because that molecule has fewer formal charges. They both have formal charges, but the one on the right has less. Okay, and whichever one has either no formal charges or the fewest formal charges, that is your best representation of the molecule. Okay, and then very, very rarely, sometimes, let's look at these two before we actually talk about it. Okay, let's do the formal charges on both of these. So hydrogen is a 1 minus 1, 0. Carbon is 4 minus 4, 0. And I'm kind of doing this a little bit quicker now. Nitrogen has 5 valence electrons, I'm looking right here, minus the 4 bonds. So the nitrogen is a +1. And the oxygen is 6 minus, and then the 6 dots plus the bond 7, so that's a -1. Okay, so that's what we have for our left molecule. For the right molecule, hydrogen still is a 0. Now the carbon, though, is 1, 2, 3, 4, 5. 4 minus 5 is -1. Nitrogen is +1, and oxygen is 0. And you go, okay, well, whichever one has the fewest formal charges, that's the better representation. Oh, wait. They both have a +1 and they both have a -1. Okay, so you should notice that each molecule has the same formal charges. They're just in different spots. Okay, the plus, I guess, didn't move, but the -1 did move. When this occurs, how do you determine which one is the best representation? Again, very, very rare does this happen, but it does sometimes. If they happen to have the exact same formal charges, just in different locations, okay, the atom that has the negative charge on the more electronegative atom is the better representation of the molecule. Okay, so here's where you have to remember electronegativity. Remember, electronegativity as you go across and as you go up gets higher. Remember, fluorine is the most electronegative element. So really, for a problem like this, electronegative. For a problem like this, just look. The negative is on the oxygen and the negative is on the carbon. Okay, which one? Basically, which one's more likely to have that negative charge on it is the one that's more electronegative. It's the one that can pull those electrons closer to itself, which means which one of those two is closer to fluorine. That's how you can think about it for a problem like this. What's closer to fluorine, carbon or oxygen? Absolutely oxygen. Okay, and so what's the preferred molecule? This one. Okay, and how would you explain that? Is exactly how we just did it. The one on the left is the better representation of the molecule, and all you would have to say is because the negative charge is found on the more electronegative atom. Done. Okay? Now, very, very uncommon, this last one. You probably won't see something like that, but clearly here's an example of that happening. What you're much more likely to see is something like SO42- or something like NO, where you're just looking at which one has fewer or more formal charges. Hopefully you might have even noticed this, but if you notice, no matter where the formal charges are found or how many formal charges they have, you'll notice that, for example, HCNO had no charge on it. There's no charge up in the corner. Okay, notice that even though there are formal charges, the plus and the minus cancel each other out. Okay, notice up here, like on SO42-, it does have a charge. That it doesn't matter which one is the preferred molecule. Combine all those formal charges together. What do you get? Well, on the right-hand molecule, what do you get? You got a -1 and a -1. That's -2. Oh, -2. Weird. Look at the left-hand molecule. You got 4 -1s, and then you add 2 to that. What do you have? You have -2. Okay, notice that the formal charges, when you combine them all together, always add up to the charge on the molecule. Even on NO, NO does not have a charge. So whether it's 0 and 0 or -1 and +1. Notice that when you combine those formal charges together, you end up with a 0 charge. That's just kind of one of the cool things about formal charges, is that the charges always add up to whatever the charge is on that molecule.